Okay, 2.3 continuity. I hope you did this in pre-calc. If you did, this is going to be a refresher, but it's not really hard, at least the idea. Okay, in order to determine continuity, first we have to know about discontinuities. A continuous graph is a graph that has no breaks. So I want to try to draw one here real quick. So the idea would be that this is a continuous graph. There's no breaks anywhere in the graph. Okay, well there are discontinuities. There are graphs that are not continuous, or some locations they have holes, or they go up to infinity, stuff like that. So I'm going to go ahead and draw them and then I'll talk about them. Okay, so here are the discontinuities. We have on the left, on the top, we have point discontinuity. This is when there is a hole in the graph. Below it, we have another example of point discontinuity. There is a hole in the graph, although they didn't make it so that there is a actual value for that x, even though it is not part of the graph. So point discontinuity, they are removable discontinuities. These are removable. And they're removable because if you think about it, or if you look at it, it just kind of looks like they take a little piece of the graph out. And because it would be so easy just to replace that little piece to make this function continuous, we call it removable. Okay, so on the other side, we have non-removable. Let's start with jump discontinuity. It is non-removable because part of the graph is actually missing in a way that, oh, let me finish that off. Oopsie. In a way that you actually have to jump from one side of the graph to get to the other side. So it's called a jump discontinuity. Just imagine being a little person here and trying to jump to the other side of the graph. That is not removable. I can't simply just replace the hole. I actually have to shift the graph. Another non-removable function is the essential discontinuity. It's the oscillating behavior. For example, the sine of x over x that has oscillating behavior. This is what it looks like. It's called an essential discontinuity. We won't see that one as much. And then last but not least, the third non-removable is the infinite discontinuity. This is usually when we have a vertical asymptote and the part of the graph just goes up towards infinity or down towards infinity, or part of it goes up and the other part goes down. But there is a break in the graph. It's not continuous. For example, if this were actually a graph, and this, let's call that 2, at x equals 2, there would be an infinite discontinuity. This graph would be continuous everywhere except for right at that point. Okay, so these are the types of discontinuities. Now, to determine if a function is actually continuous, it must meet these 3 requirements. To start you off, it's good to just list them off. But a function f is continuous at c when these 3 conditions are met. Number 1, f of c is defined. That means whatever c is, which is my x value, if I plug it into the function or if I plug it into the graph, I actually do have a value. It's not a hole. Number 2 is the limit. The overall limit exists. That means from the left and from the right. And then number 3 relates back to 1 and 2. Okay, so number 3 says that if the limit exists and it equals the same thing you would get when you plug in your x value, then and only then can you say the function is continuous. So that's the criteria we need to use to actually determine, oh, is this function continuous or not at a certain x value. Okay, example 1. Use the function f, graph below, to answer the questions. So A says, is f continuous at x equals 2? So here's x equals 2. And continuity means that it has to fulfill those 3 requirements. 1, and I'll just list them. 1 says that when I plug in my 2, I actually have a value. So I look at the graph, and at 2, I do have a value. It's right here. It's 2. 2 says that my limit from the left and from the right exists. So from the left, my limit is 1, and from the right, my limit is 1, right? So the limit as x approaches 2 of f of x here is 1. So my limit exists and it equals 1. Now part 3 says that both part 1 and part 2 have to be equal. So if I look, my limit as x approaches 2 of f of x, does it equal my f of 2? And no. The limit is 1, but when I plug in 2, I get 2. They're not equal. So is it continuous? Nope, not continuous. So you would just write not continuous. Right, next. B says, is f continuous at x equals 0? So here's 0. If you look, there aren't any breaks. There aren't any holes. If I follow along my little list here, f of 0 is 0. The limit as x approaches 0 is also 0. So then for part 3, are these two things equal? Is my limit the same as what I get when I actually plug in 0? And yes, it is. I'm just not going to write it. But then all I have to say is that yes, continuous, or just say continuous. Not making y'all do any full sentences just yet. All right, part C. Is f continuous at x equals 1? So here's x equals 1. And I look at the graph here along x equals 1. And for part 1, it says that f of 1 has to be defined. Okay, let's look at the graph. What is it? At x equals 1, my y value is 1. Okay, part 2, the limit as x approaches 1. So let's see, the limit as x approaches 1 from both the right and the left. Okay, so from the left side, here I'm going, I'm traveling, I end up at 2. From the right side, I'm traveling, I end up at 1. So my limits aren't the same from the left and from the right. So does the limit exist? No. Part 3 is supposed to be that part 1 and part 2, they're supposed to be equal. So part 3, the limit as x approaches 1 is supposed to be equal to f of 1, and it's not. So once again, not continuous. That's how you determine if a function is continuous or not. It must meet these 3 criteria. For example 2, I'm just going to discuss the continuity of each function. So for part A, this is a reciprocal function, which kind of looks like this, right? Okay, so I'm not perfect, but this is what it looks like. And I can actually determine this by finding the vertical asymptote. All I have to do is take the bottom and equal it to 0. And there's a vertical asymptote at x equals 0, which makes sense if you look at the graph. So this function is discontinuous. There is a discontinuity at x equals 0. And not just any discontinuity, it's an infinite discontinuity. Infinite discontinuity at x equals 0. All right, B. Let's see. If I want to figure out the discontinuity or continuity of this function, first I want to see, are there any holes? I can actually factor out the top to be x minus 1 and x plus 1. So then I have x minus 1 on the bottom. These factor out. The fact that they factor out means that I have a hole at x equals positive 1. And I'm left with just x plus 1. If it were just x plus 1, at the very beginning, this would be a continuous function. But because I had to factor out the x minus 1s from top and the bottom, that means there's a hole. So this function is discontinuous at x equals 1. There is a removable discontinuity. Discontinuity. All right, next. Okay, C is a piecewise function. If you remember this word from, I think, Algebra 2 and Pre-Calc. It's basically like pieces of functions put together to make like a new function or a new graph. Piecewise functions are interesting because they're actually split up into pieces. So whenever x is less than or even less than equal to whatever, the less than part is always the left hand limit. And then the part that's the greater than, that will be the stuff to the right of the graph. So that'll be the right hand limit. And here at this function, the point in question, the point that's like of any concern to us, is here at x equals 0. Now if you look at the piecewise function, only one part of this function actually involves the number 0. And that's the part that says less than or equal to, because of the equal to part. The other part doesn't actually involve 0. So if I want to figure out the continuity of this function, I'm going to have to actually figure out the whole limit thing. So let's do the limit as x approaches 0 from the left. So I'm going to use the top part. So let's see, I'm going to plug in 0 plus 1. Okay, my limit is 1. Now, oh, sorry, I skipped like a whole part here. This is h, not f, h. H of x. Okay, so 0 plus 1 equals 1. Now if I do the limit as x approaches 0 from the positive side, so that means I'm going to use the bottom part of the function. I have 0 squared plus 1. It's also 1. So my limits are 1. That means my overall limit, the overall limit as x approaches 0 of h of x is 1. So that right there is part 2 of my criteria, right? Part 1, and so what if I'm doing it out of order? No big deal. Part 1 says that if I take my function h and I plug in the 0, it has to be defined. So again, I'm going to look at the top part because this is the part that actually involves 0 because of the less than or equal to part. So let's see, 0 plus 1 equals 1. And then the third part of the criteria is that my limit should equal my h of 0. And these are equal, so this function is continuous. Alright, please write this down and stuff because I need, well, never mind. I'll just squeeze D in. D, it's really simple to answer if you know what the function looks like. Um, the sine function looks like an S. You should have learned this in pre-calc, right? I'm going to look something like this, and it just keeps going and going and going in both directions infinitely. So this function is continuous. Okay. All right, example 3, determine if the functions are continuous. So again with my criteria. So 1, for this function f, I need to make sure that at this value, x equals 1, I actually have something. It's defined. So if I look at this piecewise function, add x equals 1, this is this part. When x is 1, the graph actually equals 2, or my function equals 2. Okay, part 2. The limit as x approaches 1 of this function f of x must exist. So here, this is just a point. This is a point off in the air somewhere. So if I want to know what the limit is, I'm going to use the top part of the piecewise function, and I'm going to plug in my 1 there. So 3 times 1 is 3 minus 5, and that's negative 2. So hopefully you see the problem already. So part 3 is that the limit should equal whatever I get when I plug in 1. And as you can see, I got negative 2 here, and I got positive 2. So that's not true. So this function is not continuous. We're going to do the same thing for the next problem. So for b, again, a piecewise function. Here are my x values. But remember, piecewise functions have lefts and rights. It's already kind of split up for you. So the first one, the top one, says x is less than or equal to negative 2. So less than means that's the left-hand limit. And then the bottom is going to be the right hand because x is greater than, so negative 2. So that means all the numbers to the right. So right hand. And again, just going to do the same old criteria thing. 1, when I take my function g and I actually plug in my x, which is the negative 2 part, I should get a value. It should be defined. Right, I need to figure out what part of this piecewise function is the part that I can actually, or I'm supposed to, plug in the negative 2 to actually get a value. And hopefully you can see the less than or equal to part because of the equal. So I plug that in to the top part. So negative 2 squared plus 2 times negative 2. And let's see, what do I get? Negative 2 squared, that's 4, plus 2 times negative 2, which is a minus 4. So I get 0. Okay, part 2 is that the limit must exist. The limit as x approaches negative 2 of g of x. So the limit means that I have to take the left hand and the right hand limit, and they must be equal. So let me go ahead and do that. I'll do it on the side here. So let's see, the limit as x approaches negative 2 from the left side. That means I'm going to plug it into the left part of the piecewise function. Oh, but wait, we kind of already did that. The left-hand part is the top part, and for 1, we kind of already did that, so I know that this is going to equal 0. I'm just saving you steps. All right, now I need to do the limit as x approaches negative 2 from the positive side, or the right-hand limit. So this time I'm going to use the second equation. We haven't done that yet, so I'm actually going to have to do this. Negative 2 cubed minus 6 times negative 2. Let's see what I get. Negative 2 cubed is negative 8. 6 times negative 2, or negative 6 times negative 2, I can use it that way. It's positive 12. and I get 4. Okay, so one limit is 4 and the other limit is 0. So this limit doesn't exist. Do I need to move on? Do I need to continue to step 3 to determine already that this is not continuous? No, you don't have to actually show me, well, right now, that 1 and 2 are not equal. Obviously, does not exist, does not equal 0. So this function is not continuous. All right, example 4, making a function continuous. So for what values of k is the function continuous? In this example, I have a piecewise function, but I have k here instead of a number. What they're trying to do is they're trying to get you to figure out what could that number be that would actually make this function continuous. So we're missing the number, we're trying to find that number. Okay, so this is my x value, right? X equals 3. There's a left and there's a right. So this is the left and this is the right. But the idea of continuity starts at the fact that not only do I have to plug in the 3 into some part of this and get a number, but my limits have to exist. If my limits don't even exist, then there's no point in doing anything else. So the idea would be, and to solve these kind of problems, all you have to do is make sure that the left and the right hand limits are actually equal, and then you can find out what that missing value is. So it's just as simple as taking the left and setting it equal to the right, because I know for a fact that my limits must be equal. So if my limits are equal, then these pieces need to have the same value. They need to be equal. They need to equal the same thing. So just set them equal to each other. Okay, now that I've set them equal to each other, my x value is 3, right? And I determined that from the information in this box here. So now I can actually go ahead and plug in the 3 into this equation that I've written out. So I have 3k, because instead of the x, I'm plugging in the 3, plus 1 equals, let's see, 3 squared, so that's 9k minus 1. And then you solve like regular old algebra. So let's subtract 3k from both sides. Minus 3k minus 3k. And now I have 1 equals 6k minus 1. Let's move up a little. Add 1 to both sides. And I get 2, oopsie, equals 6k. Divide both sides by 6. And I get k equals 1/3. And this is the value that I can put into the equation instead of k that would actually make this function continuous. This example is just like example 4, only that if you look at the piecewise function, it grew. I have 3 pieces now instead of just 2. It's the exact same idea, only that this is going to involve systems of equations, and I have a left and a right, but then I have another left and a right. So it says determine all values for a and b so that the function is continuous for all values of x. Okay, so here I have 3 pieces in my piecewise function. The top and the bottom, they share the number -1. So the top is going to be the left, and then the bottom is going to be the right. And I'm going to use the value x equals -1. Now, The second piece and the last piece, they share the number 1. So for those two, the middle one is going to be the left-hand limit, and then the bottom one is going to be the right-hand limit. And for these, I'm going to use x equals 1. So I'm going to do basically the last example, but just twice. So I'm going to start with the first two. The idea is that I can figure out what A and B are as long as those two pieces are congruent or equal. Sorry, geometry talk. So ax minus b has to equal 2x squared plus 3 times ax plus b. So I know that my x is negative 1, so I'm going to go ahead and plug it in. So I have negative a minus b equals 2 minus 3a plus b. All I did was plug in the x equals negative 1. If you look at this equation, it's kind of yucky. I still can't solve this because it has two variables. So you leave it alone for now, and you move on to the other two pieces of the piecewise function. Or not the other two, but the next, the blue part. So I'm going to go ahead and split this up here so that you can see. All right, so I'm going to do now the middle one, 2x squared plus 3ax plus b. That now needs to equal 4. So now I'm going to go ahead and plug in my x, which is equals to 1. So 2 times 1 squared, so that's 2 plus 3a plus b equals 4. So again, I have two variables. I have two variables on both equations, but I have two equations, and that's systems of equations. So I like substitution. I like elimination also, but substitution is usually just the easiest way to go. So I'm going to use substitution. In order to use substitution, I have to get something to substitute. So what I'm going to do is I'm going to work on this blue equation because it looks nicer. It's prettier. It's smaller. It doesn't look as complicated as the red one. And I'm going to get b by itself because b looks like a good candidate. Doesn't have any numbers being multiplied with it. It's not squared. It's not anything funky like that. So minus 2 from both sides. Minus 2. Minus 2. I get 3a plus b equals 2. Again, I repeat, I'm trying to get b by itself because it looks like the friendliest one to do. So I'm going to go ahead and subtract the 3a from both sides, and I'm going to get b equals 2 minus 3a. So now I have a value for b. All of this stuff right here is equal to b. So what I'm going to do is I'm going to take that stuff and I'm going to plug it in to this equation. And that's what substitution is. Wherever there's a b, I'm going to replace it with 2 minus 3a. Okay, so let's see, negative a minus 2 minus 3a equals 2 minus 3a plus 2 minus 3a. And now I can simplify, and I can actually solve this equation because I only have one variable instead of two variables. So let's see, negative a minus 2 and then plus 3a, because this negative got distributed to both of these, equals, let's see, I've got a 2 and another 2, so it's 4. And then I have a negative 3a and another negative 3a, so that's a total of negative 6a. I would move, let's see, what am I going to move? I'm going to move, well first, sorry, negative a and 3a, that's just 2a. So negative 2 plus 2a equals 4 minus 6a. All right, now I'm going to move something, and I've decided to move the 6. So plus 6a and plus 6a. And at the same time, why not? Let's save ourselves some steps. Since I moved the a's to the left, I'm going to move the 2 to the right. Okay, so this cancels out, and this cancels out, and I end up with 8. Oops, that's green. and I end up with 8a equals 6. Divide both sides by 8. I get a equals 6 over 8, which is 3/4. And now I know what a is. A is 3/4. I still don't know what b is. So I take what a equals and I plug it in over here. It's kind of like a zigzag going on here. So b is going to equal 2 minus 3 times 3/4. So I get 2 minus 9/4. So basically this is 2 minus 2.25. So I get negative 0.25 or negative 1/4. The last example involves sketching, and when I say sketch, it means not Pablo Picasso. Try your best to make these sketches, at least clean enough so I can understand them. So sketch a possible graph for a function f that has the stated properties. So there's 3, so I'm going to graph 3 times. I'm going to go ahead and draw like the axes. So hold on. Okay, so A says f of 5 exists, but the limit as x approaches 5 of f of x does not. So I have to try to sketch that. So the easiest way to do this would be, let's say my graph was going by 5s, and this is 5 right there. So f of 5 exists. That means I actually have a value. Okay, well, let me decide to make the value right here. That is the value of f of 5. The y value doesn't really matter. I don't care what it is. This is just a sketch. Now the limit does not exist. In order for the limit to not exist, that means the left and the right-hand limit must be 2 different things, right? So try to sketch a graph that will end up with 2 different limits. And I like the idea of this. That graph coming in from the left actually ends up at 5, but then maybe from the right, it's somewhere down here. And there you go. That's a jump discontinuity, and I have sketched a graph with the criteria given to me. All right, B says f of negative 2 exists. The limit as x approaches negative 2 from the right side of f of x equals f of negative 2, but the limit as x approaches negative 2, the overall limit, the big kahuna, does not exist. So once again, that means I have a different left and right-hand limit, but here it's telling me that my right-hand limit is going to be equal to whatever my f of negative 2 value is. So here's negative 2. Let's say this right here is what my f of negative 2 equals. And my right-hand limit needs to be the same as that dot. So here's the right part of my graph. Now the left part of my graph is not allowed to be the same height as my right part. So here, there's my sketch. It's not beautiful, not gorgeous, nothing special, but it does actually fulfill the requirements specified to me, that the left-hand limit, which is all of this stuff over here, is different than my right-hand limit, and my right-hand limit does actually equal the f of negative 2. Okay, C, f of x is continuous for all x except x equals 1. So at x equals 1, something's happening. Where f has a non-removable discontinuity. Okay, so the last 2 I did were non-removable, but this one doesn't really say anything other than that the fact that it is continuous everywhere except for at x equals 1, and it has to be non-removable. So I can't make it point discontinuity, which is fine, but I think I want to use one that I haven't used yet. So at x equals 1, let's pretend we have a vertical asymptote at x equals 1. And if that's the case, then let's say that my graph looks something like this. It is non-removable. It's actually an infinite discontinuity, and um, my function is actually continuous everywhere except for x equals 1. Okay, that's it. Please do your homework. Try your best. These problems are more similar to the ones in the book. They're not as bad as the last homework. Okay, test next class on 2.1 and 2.2.